All right, time for problem 3, Haybale distribution. We have Farmer John's farms. He has n farms where n is at most 2 times 10 to the 5, located at integer points along the number line where all the points are between 0 and 1 million. Farmer John's plan is to have n shipments of hay bales delivered to some integer point y, and then distribute 1 shipment to each farm. Unfortunately, there is some wastage going on. So for some coefficients AI and BI, AI hay bales are wasted per unit of distance left every shipment is transported, and BI hay bales are wasted per unit of distance right each shipment of hay bales is transported. We're going to assume we have enough hay bales such that even with the millions that are wasted, by the time the shipments arrive at their barns, we still have enough hay bales left for the cows to hopefully eat. So I'm going to draw a little diagram here. There's some math, but I'm going to do this visually. So we have a number line here from 0 to 10 to the 6, and there could be 10 to the 5 farms dotted along this path. I'm just going to draw a few. So let's assume y is over here. It lands at this exact point. So how many hay bales are we going to waste? Well, we're going to add up all of these distances, which are the distances that the hay bales need to be transported left, and we're going to sum those together and then multiply them by AI, because AI is the number of hay bales wasted per unit of distance left, and then for every unit of distance right every shipment is transported, we're going to waste BI hay bales. Once we add them up, we're going to get our total wastage. We're going to be given Q different queries where for each query we're going to get a value of AI and BI, and then we have to figure out the minimum possible wastage if we place Y strategically. The overall strategy is we're going to find a fast way to compute for every single drop point the total number of hay bales wasted. If we know A and B, we're going to pre-compute all of that information ahead of doing any queries at all. And then it turns out the wastage graph actually kind of looks like this. It is a convex function that has a global minimum somewhere at the middle. And this is true no matter what values of AI and BI are chosen, as well as where the barns are. So this doesn't matter at all. It's going to be a convex function that looks like this. It has a global minimum, and we're going to find that minimum using ternary search, we'll explain in a little bit. But I kind of guessed this was true and did a bunch of random test cases, plotted them with a bit of matplotlib, and the shape looked right. I didn't want to prove it, but it just works. I'm going to explain that in a little bit. So onto the code. We're going to first pre-compute DL and DR. These arrays are going to store the total distance to all of the left barns and the total distance to all of the right barns for every single barn. For DL, we're going to process the barns from left to right, and then for every single barn, we will have the previous barn's information. So let's say we have barns at these points over here, and this is barn I minus 1. We're going to have the answer that is the sum of the distances to all of the previous barns. And then for barn I, we're just going to have to add a few new distances, which are these right here. It's exactly the distance from I to I minus 1 times the number of barns that have appeared already. So that's exactly what we do in this for loop. The same thing happens for DR, which is the sum of the distances to the right barns for every single barn. And we're going to compute those from right to left using generally the same tactic. Once we have that information, we can write this function called cost, which takes a point y on our number line, as well as the coefficients a and b. This allows us to write a function cost, which takes in parameters y, as well as coefficients a and b. Now, the idea behind this function is once we have a coordinate y, we will have all barns to the left and all barns to the right. We will know the sum of the distances here, as well as the sum of the distances here. And all we need to add to that is this distance times however many barns are to the left, plus this distance times how many barns there are to the right, where each of those are weighted by AI and BI. What I did here was use C++'s handy dandy function upper bound and lower bound, which basically helps you binary search within a sorted list for any coordinate you want. So we're going to find the closest left barn using the upper bound function, and we're going to operate on the list of coordinates of the barns, and we're going to do the same for the index of the rightmost barn. There is some off by one stuff here. You just kind of have to fiddle around and determine what the right answer is. Now we know what the closest barn to the left is and what the closest barn to the right is. For all of the left barns, we're going to add up those distances by taking DL of the closest barn to the left. That's going to give us this group over here. We're also going to add all the distances over here, because to get from Y to that left barn, we're going to have to move all of these shipments. There's going to be IDX low plus 1 of those, because for example, if you have 0, 1, 2, 3, 4, there's going to be 4 plus 1 shipments that we need to move to that leftmost barn first. For each of those 5 shipments, they're going to need to move a distance of y minus x of IDX low, which is just the distance between Y to the closest left barn. So we do that multiplication, we add that to the DL value. There's a bit of an edge case over here, which is if upper bound returns a value of 0, then we're going to subtract 1. There's some off by 1 stuff, and we're just going to make sure it's not negative. We're going to do the same stuff for the closest barn on the right. We're going to take all of these shipments, we're going to move them a distance of X IDX high minus Y. That's the distance to move all of those shipments to the closest barn to the right, multiply that by the number of shipments to get that distance moved, add the corresponding DR value, and then we're going to have cost L and cost R, which are the total net distance we need to move for all of the shipments going left and all of the shipments going right. Once we have those, we weight those by A and B, and then our function is done. Now all of the pre-computation is sort of done, and we have an O log n way to find the total cost if we drop a shipment at Y and we're given A and B to deliver all of the shipments to the barns. And when I say cost here, I mean hay bales wasted. Now that we have our cost function, we're going to use ternary search to find our answer. Now, as I mentioned previously, this function is going to be kind of convex. Actually, it is convex. Just empirically, I tested a bunch of test cases and it was convex. This function is, of course, Y versus cost, and basically this is where are we dropping it, how many hay bales are we going to waste. We want to minimize that function. So we're going to start out with a range low to high of possible Y values that we could search through. We can't search through all of them iteratively because Y is between 0 and 10 to the 6, and if we did 10 to the 6 times the number of queries, which is 2 times 10 to the 5, that's way too big. So we need a way to search through the space logarithmically, and ternary search is going to allow us to cut down on this space by a factor of 2/3 at a time. So initially the range is 0 to 10 to the 6. We're going to cut down on 1/3 of this for every iteration of ternary search. So we have low to high. What we're going to do is cut this into thirds. We're going to pick out points C1 and C2 and evaluate the functions at those points. So F1 and F2 are going to be those values. From I, we can immediately see that this third C2 to high is what we're going to cut out because the minimum obviously doesn't lie in this range. But algorithmically, what we're going to do is we only have the information of what is low, what is high, what is C1, what is C2, and what are the values of the function at those points. So we have low and we have high and we have C1 and C2, and we know what the values of the functions are there, but we don't know what the function looks like in between. Now, since it's convex, the function sort of kind of has to look like this. There's no way the minimum can be between C2 and high, given that C1 is less than C2. So the function would have to look like something like this in order for the minimum to be between C2 and high, and that just doesn't work for a convex function. Because what a convex function is if you draw the curve and you draw any line segment between 2 points on the curve lies between that line segment. So on the other hand, if we have the cost at C1 as greater than the cost at C2, then we're going to be able to cut out this third, because then the function would have to look something like this, which is definitely not convex. In either case, we're going to have the values of the cost function at C1 and C2, which we find using our handy dandy logarithmic time cost function. If the value at C1 is greater than the value at C2, we're going to cut out the lower third by assigning low to C1. If the value at C1 is less than the value at C2, then we're going to cut out the higher third by setting high to C2. And then we have some edge cases here. Basically, if it's like flat, then we're going to compare the 2 points. If they're equal, then we have our answer. After this while loop is done, we're going to have high and low, which are the endpoints of our range. Either they're going to be the same number, in which case we have our answer, or they're going to be separated by exactly 1, in which case we can just evaluate the function at both of these points and see which one is lower. So that entire ternary search is going to take log base 3 halves of this entire range, which is 0 to 10 to the 6, and let's actually see what that value is. Looks like it's about 34, so we're going to do roughly 34 iterations for every single query, and for every single iteration we're going to take log n time, because we need to evaluate the values of the function at C1 and C2 using our cost function, which is log n time, and log 10 to the 6 base 2 is roughly 20. So 20 times 30, that's roughly like 600 operations per query, which is definitely going to fit within the time limit. So yeah, that's problem 3. Moral of the story here is ternary search is an incredibly powerful tool when we have convex functions and we're trying to find the minimum or the maximum, and pre-computing a bunch of stuff is really helpful when we need to do those kinds of searches, because it allows us to compute the values of the function at exactly 1 point. More specifically, if you ever need to compute cumulative distances to various barns along a number line, say, then precomputation can be really helpful. But overall, I hope you enjoyed my explanations of the problems and got something out of it. If you want to check out my code, it's going to be linked to in the description. I'm going to upload it to GitHub, so be sure to check that out. If you have any questions or comments, feel free to leave those down below. Thanks for watching, and I'll see you in the next one.